sometimes we also have to model the systems as a second order instrument or sensor. This choice can actually depend on you know, which kind of model you will use. That may depend on physical reasons, or it may depend on the kind of response that you actually get from the instrument. So some instruments are rather assumed to be governed by a second order differential equation. For example, accelerometer, anything which has you know, mass spring damper kind of representation, and we'll have second order dynamics. So its dynamics, its input output dynamics is given by a second order differential equation as shown, in which there are two parameters. One is called a natural frequency, another is called a damping factor. So again, its response to the step input. In this case, we have three kinds of cases depending on what is the damping factor. So one case is when the damping factor zeta is greater than 1, in which case we call it an overdamped system, and this is the expression for the output time function. We will just see the case and then we will see the plots. So, and then we have a case when xi is equal to 1, zeta equal to 1, which is called the critically damped case. Here and the last case is when we have xi is less than between 1 and 0. So that is called the underdamped case. So the plot actually looks like this. So this is of interest to us. So you see that this is the step response. So the input applied is this. This is the input. Now for different values of zeta, for example, if as zeta goes to lower and lower values, you can see that you get an oscillatory behavior. So there is an overshoot. This is called an overshoot. So for underdamped sensors, you are going to get an overshoot. On the other hand, for overdamped systems, there is no overshoot and it slowly rises, just almost like a first order system. Similarly, if you see its response to a sinusoidal input, again you will find that these are the expressions. So you get a gain and you get a phase shift, and this is the expression for, this is the plot for gain. So you see that the gain actually changes with frequency, right? And for underdamped systems, the system tends to resonate. So this is the resonant frequency. So if you give a sinusoid close to the resonant frequency, then you get a huge output, right? Well, on the other hand, for overdamped system, there is no such resonance. So you have similarly the phase. If you see the phase, the phase plot looks like this, again with frequency. So towards low frequency, the phase tends to stay small, and as frequency increases, so the maximum phase that can occur is 180 degree. So these are the phase lags.